All right, hello, math nerds. It's the Crazy Master Nerd coming out at you on our series of videos about volume. All right. So the last couple of ones that I did that you may have seen were all about the big concepts of finding volume and using your calculator to answer your questions. Today's video is about doing this by hand. And one of the hardest things about doing a volume problem by hand is actually finding the region that you're going to revolve and revolving it correctly. So let's practice that. And so this is from number 3 Master Math Mentor, and we're going to go around an x-axis, a y=4, which is an x-like axis, and a y=5, which is another x-like axis. So all of these are x or x-like axis, so all of our functions will be in terms of x, and all of our limits will be in terms of x. And that is going to be important because in the next video everything will be in terms of y. So kind of crazy, huh? All right, so let's draw the picture of y=x squared. Okay, so I'm just going to kind of do a parabola. I'm not going to do the other side because I'm not going to need it. Y=0 is going to be the x-axis. And for those of you who have a hard time with that, remember, anytime you have a variable equal to 0, it's the other axis. That helps me kind of when I'm thinking real fast. So y=0 is the x-axis and x=0 is the y-axis. It kind of helps me. And the line x=2. And we're just going to call this right here x=2 for our purposes today, which means this would be y=4 right there. There you go. So now I'm going to highlight the area that we're going to rotate. And of course, I'm doing it in pink, my favorite color. And a lot of the other areas that we rotated when we used that calculus of motion was in pink too, so that's kind of cool. All right. It says I'm going around the x-axis, so I'm going to indicate that I'm rotating around the x-axis. That was kind of bad, but anyway. All right, and then I'm going to actually attempt to do that. Here we go. Be nice, right? And notice that when I rotate it like that, that if I filled in the other side, that this whole solid is flush to the axis that it is going around. And so that means that there is not that hole in here, right, because we're on that. There's not a hole in here, so we will have cross sections that look like discs or that look like frisbees. And so when you hear, and I'm going to take the S off, when you hear people say the washer disc method, that is what they're talking about. When you slice part of the solid, and I know that's a wobbly circle, sorry, and you get a circle and it's solid, it looks like a frisbee, and so we call that a disc, okay? All right, so we're going to add up infinitely many areas of circles. That's what we're going to do. With respect to x, because we have an x-axis that we're rotating around, and we're going to go from 0, and we have to do this in terms of x. We're going to slice all the circles from 0 all the way to 2. And we're going to add up all the areas, and when we do, we'll get the volume of this solid. And so I've got to figure out what r is, the radius. And the radius for all of these discs is from the axis of rotation out to the function in question, and that is x squared. So all of the radii are different, and they vary as this function varies. So we're going to rewrite it in terms of our function. So 0 to 2, we're going to take the constant of integration out, and r is x squared squared. So because we're doing this by hand, we're actually going to integrate by hand. So here we go. This is x to the 4th. It's going to be x to the 5th over 5. Evaluated from 0 to 2, and let's put that constant out front. When you plug in 2 minus plug in 0, you get 32. That's going to be 32 fifths over pi, and that's the volume of that solid. So it looks like a crazy, weird horn thing. Okay? All right. So now we're going to look at the next problem that's going to go around the line y=4. And because that's going around a line that's higher than this, because that would be that line right there, we're going to take another screen so we can actually rotate. So, oh, look, she's drawn for us. Yes, I have. So I've already got our region. It's the same region. So I could kind of prep this beforehand because this is x squared, right? And this is x equals 2, and that's 0. And so now instead of going around the x-axis, we're going around an x-like axis because it's parallel to the x-axis. It looks like it, right? Remember, y equals number is an x-like parallel thing. I know, crazy, right? And so because we're going around an x-like axis, I actually reflected the area. There it is. What we're going to do is you always have to think about this in terms of the axis of rotation. Like what are your radii in comparison to the distance that the area is from your axis of rotation. So you look at that. I'm going to attempt to draw, so be nice. If I try to do a slice, notice that if I try to slice through, there is a hole in the middle, like our donuts we've talked about, right? So we have to do the area of the outside circle minus the area of the inside circle. Go back to my donuts, I love those. It's the whole donut. Now I can't say that, right? It's the entire donut minus the whole of the donut would give us the area of the donut we get to eat, right? You got to remember that. And so what we're going to do is we've got to figure out what this outside radius from the axis of rotation is and the inside radius from the axis of rotation. What is that distance? Okay, I'm actually going to now take that little disc thing out that I just drew because it kind of impedes us seeing it. So we're going to add up all of the areas from 0 to 2 of pi, and I'm going to look and see what is the distance from the axis of rotation to my most outer edge. So I'm going to draw this. My most outer edge. What is that distance? And you can see I've labeled over here that is a distance of 4 because this is y equals 4 and that's the axis. And it doesn't change because for any of those radii you draw, see how that's flat? It's a constant value. So that is 4 squared, pi r squared, minus pi. And so now we've got to figure out what is the radius of that. Oh, I don't want to do that. I just want to erase it. What is the radius of this little bitty inside circle? I'm going to try to erase it best I can. Okay. So from the middle out to here is the radius of the inside circle. Let me do a different color. I don't want to do pink though. Let's find. No, let me find another color. I know. How about purple? Okay. It's going to look just like that pink. And anyway, I'll just make it real dark. I want to find, that is the radius of the inside circle. So how much is that? Well, it changes. That one's going to be different than the one right here, right? That inside radius. So I do know that this inside radius is dependent on the function somehow. But notice it's not the distance from the function to the axis. Matter of fact, this radius is going to be dependent on the function, but it doesn't need that height. Like the height of the function is not part of that inside radius, so we actually need to subtract that out of that. And so the radius is 4 minus the x squared. See, the big 4 minus the x squared really gives you that inside radius. And if you actually do all the squaring and integrate it and everything, you do get the answer of 224 pi over 15. And I'm going to let you work that on your own. I did want to give you the answer, but that's kind of what would happen. Okay? So the next problem is going around y equals y equals 5. All right? Same situation. Because it doesn't really matter if it touches or not. It's still that same distance away. I did not draw the reflection and everything because this is so similar. So we're going to add up from 0 to 2, and this time I'm going to get crazy and put that pi out to begin with. The big radius is going to be from the axis of rotation, which is here, the axis of rotation, out to the most outer edge of the area, right? The most outer edge. Go down, which is 5. So that's big R squared minus little r squared. Pi r squared minus pi r squared. So we're just doing areas of circles. And notice that if I want to do the inside guy, and I'm going to erase that. Erase this little part. If I want to do the inside guy, then I just need, and we'll do the purple again because I like purple. This looks very similar to the one we just did. This radius goes down and hits the function, but it doesn't have the function's value from 0 to x squared there. So this is actually going to be 5 minus x squared squared. So the distance from here all the way to the ground is 5, but we don't get all the way to the ground because we don't have that y value from the axis up to the function, which is x squared. So 5 minus x squared gets us to the length of our inside radius. And if you figure that one out, you will end up with 304 over 15 pi. Okay? So that is doing this by hand, doing volume by hand, going around an x-axis or an x-like axis in which all of the limits and functions are in terms of x. In the next video, we see what happens when you're asked to go around a y-axis or a y-like axis. Hope this has been helpful. Thanks and have a great day.